module, look, let's go ahead and take really some more examples. Okay, so here we've got a circuit here. We've got V of S, I of S, and we've got the ZT, the total impedance. Now, in this case, we're given I of S, that's 4 milliamps, angle 15, and we're given V of S, that's 10, angle 45. And we want to find, once again, the apparent power, the real power, and the reactive power. Well, look, before we start, let's just look at a little diagram here showing the angle relationships of this voltage and current. So we've got Vs looking like this, right? So that's Vs, and this angle here would be what? 45. And then we've got Is, well, that's kind of sitting here, isn't it? There is Is, and this angle over here is the 15 degrees, all right? Now, once again, for these calculations of complex power, we're interested in the angle difference between that Vs and that Is over here. All right, so let's go ahead and calculate the apparent power S. That is equal to what? It's equal to Vs times Is, but the complex conjugate of Is. So that is what? That's 10, angle 45, and that's multiplied by Is, but the complex conjugate of Is, which is 4 milliamps, and my angle over here is 15, but it's a minus 15, isn't it? So when we work this out, what we get then is the apparent power being equal to what? That's 10 times this number here, which is 40 milli, and that's volt amps, and my angle over here, that's 45 minus the 15, which gives me an angle of 30. Now notice that angle of 30 is the angle difference, is it not, between this voltage and this current over here. All right, so that is the apparent power. So next step, we could actually look at the power triangle. And as far as the power triangle is concerned, let's plot this. We've got the real power, we've got the reactive power, and of course we've got the apparent power. So that's S, that is Q, and of course that is my real power over here. So look, and this angle of course is what? It's the angle difference here, which is that 30 degrees. And so what we can say then is that my real power is equal to what? It's equal to the S, which is this 40 milli VAs multiplied by the cosine, right, of 30 degrees. And if we work that out, we get that the real power is equal to 34.64 milli, and the unit over here would be watts. Okay. Reactive power Q is equal to, once again, that 40 milli VA times the sine of that 30 degrees, and that is equal to, so we work that out, that is equal to 20, and that's milli, and the unit volt amp reactive, okay? And so really we've now been able to work out everything. Of course, we've got our apparent power, we've got our real power, and we've got our reactive power. Now, we can say that the circuit here is what? It's inductive. Why? Well, it's inductive. We can look at it from two ways. We can say it's inductive because the current, right, the current here is lagging the voltage, okay? Or we can actually say that the real power is actually lagging the apparent power. And so really the power factor here, the power factor, right, which is equal to the cosine of that angle of 30 degrees, that power factor is a lagging power factor. All right, let's look at another example. Once again, we've got Vs, we've got Is, and we've got a total impedance ZT. We're given in this problem, Is is equal to 8 milliamps at an angle of 80, Vs is equal to 10 angle 20. All right, let's just show that information on a graph. So once again, here we are. we have got IS. Let's draw IS here. So there is my IS. This angle over here, what is that? That's that 80 degrees. And then VS, well, that's kind of sitting down here, isn't it? And the angle here is 20 degrees. Now you'll note in this case, really the current is actually leading the voltage. So the current actually leads the voltage. And you remember that little acronym thing that I showed you before, civil? Well, in a capacitor, the current is leading the voltage, and so we could say that this circuit here is capacitive in nature. Okay, so it's capacitive in nature. All right, once again, we're trying to find the apparent power, we're trying to find the real power, and we're trying to find the reactive power. So we can say that the apparent power S is equal to what? It's equal to this voltage, which is 10, angle 20. That is multiplied by what? IS, but the complex conjugate of IS, so that's 8 milliamps. And the angle here is what? It's going to be a minus 80 degrees, is it not? Okay, so let's do this. That comes out to be what? That's 80, and that's a millivolt amp, and that's an angle. So we've got plus 20 minus 80, that's a minus 60 degrees. All right. So at this point now, we know what the power factor is. The power factor basically is the cosine of that minus 60. We could draw a little power triangle again. So power triangle. And what have we got? Well, we've got our real power. We've got the reactive power Q, and we've got our apparent power sitting here, which is S. And the angle we're talking about here is this minus 60 degrees. Okay? So knowing this triangle now, or knowing the power factor, we can say that the true power is equal to what? It's equal to the 80 milli VAs multiplied by the cosine of this minus 60. And if we work that out, that is what? That is 40 milli, and of course the unit being watts. Okay, we can say that the reactive power Q is equal to, again, 80 milli VAs at sine now of this minus 60, and we can say that that is equal to a minus 69.28, and that is a millivolt amp reactive. Okay? And once again, the minus sign here indicates really that the circuit really is capacitive in nature. And we say that really because the current leads the voltage, or we can talk about the real power leading the apparent power, we can say that this is a leading power factor. All right. What I'd like to do now is leave you with a problem. We have a circuit here. Okay, so we have a source voltage here, which is 250 angle 0. And then we have basically a line impedance. Okay, this is basically the impedance really associated with the wires that connect to the load. And we're saying that that is really 1 ohm here. It's inductive, and it has a value of J4. Okay, so this is really the line impedance here. Then we have our load over here. This is our load impedance, which is a real part, 39 ohms, and then we have our reactive part being J26. What I'd like you to do, all right, is find the current IL in this circuit. I'd also like you to find that voltage VL that's across the load. Then what I'd like you to do is find the reactive power in the load. Find the real power in the load, and then find the apparent power in the load. Next, what I'd like you to do is find the reactive power in the line, the real power in the line, and the apparent power in the line. And then finally, calculate the reactive power supplied by the source here, the real power supplied by the source and the apparent power supplied by the source. All right, look, give it a go, and I'll see you next time.